Hello and welcome to Lab 2, Magnetic Field of a Bar Magnet for Physics 2212. This is Jessica Cruz. Introduction. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet using a magnetometer. Some of the fundamental principles are listed below. Biot-Savart law, on-axis formula, and perp-axis formula. The formulas are to the right, and I have also included the magnetic dipole moment formula. My results are down below. I got the magnetic dipole moment to be 2.25 and the distance dependent to be negative 3.62. Systems and surroundings. The system is our magnetometer and our surrounding is a magnet and earth. Assumptions. The bar magnet can be treated as a magnetic dipole. Earth exerts its own magnetic field on the magnetometer, which we must account for this. Initial conditions. The magnetic force of the Earth acts on the magnetometer. Errors. Possible errors were that there could have been any rounding errors or there were some inaccuracies with our magnetometer. And what a magnetometer is, it's just a device that measures magnetic field or magnetic dipole moment. Procedure. First, we had to calibrate our magnetometer using a ruler, tape, and bar magnet. We then had to measure the magnetic field of a bar magnet at different distances with a magnetometer. We had to collect data and calculate distance dependence. We then created a computational model in GlowScript, and we then compared our experimental data to our expected data. Experiment. Here I have my experimental value, my computational value, and some possible experimental errors, such as the magnetometer may be inaccurate due to other forces. By this, I mean that I might have had jewelry around, I might have had another phone, another device or something that made the magnetometer inaccurate. As you can see, here are my results and what I listed for this experiment. And we can see the line of best fit, which is this right here, and the equation I got for it. Coding. For the coding, obviously we have our variables, which was u epsilon over 4 pi. And then we created the magnet at the origin. And then we created a function for the magnetic field. And then we created we created arrows like the scaling and observation locations. We then created our arrows, and the arrows represented the two different equations. And yeah, our result was this for our coding. Questions. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, which is true. 2. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. That is false. It does not decrease, but it increases. The position of the magnetometer has no effect on the measured x component of the magnetic field. This is false. It does have an effect on the measured x component of the magnetic field. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, which is true. And here were our additional questions. At first, what if you hadn't done that and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The non-zero x component will not let us account for the changing numbers and will more than likely make our data invalid. What if you redid the experiment, but instead of using a single magnet, you used the two identical magnets stuck together end to end? How would you expect your measurements to differ? The stuck together magnets will point in the same direction, but will have different magnitudes. Therefore, to reiterate, measurements will be the same, but magnitudes would probably be different. Thank you.